We'll talk about an oscillator first, because oscillators are awesome and they're great stepping stones and test beds. And that can be the system that the qubit interacts with. It can also be the qubit. So by engineering the oscillator correctly, we can make it both a readout cavity and use it as a readout resonator to read out the qubit. We can make the qubit out of it. We can make it into an amplifier. We can make several oscillators into several qubits and entangle them and control them in very interesting ways. But the essential ingredient is the oscillator. So this is why I'll spend some time on the quantum harmonic oscillator. And I will only very briefly introduce here. Last time I spoke about some of this, there was a lot of questions about how do you take the bridge between all the classical stuff we just said and the quantum. And so I'll do a dangerous bend ahead on quantization. This is slightly more advanced, 2 slides, and I wanted to expose the more interested of you on how you make this transition from the classical world over here through a barrier into the world of quantum, where we have Schrödinger kitten states, cat states, and things are a little more fuzzy. And perhaps my story here begins with Paul Dirac. Paul Dirac observed something very interesting. He said Heisenberg's had very early on derived the commutation relations for Heisenberg operators, and he had also done the Heisenberg uncertainty relationship. And essentially we knew that quantum operators in the Heisenberg picture can be described like this, where position and momentum, x and p, commute to 1 modulo some prefactor, and the time evolution of a quantum operator O is given by the quantum commutator between operators, the operator and the Hamiltonian operator. Now, he observed that in classical physics there is a particular way to write things where there's this other notion of a Poisson bracket, and again I'm going to exploit here some more advanced terminology. It's some kind of operation, a Poisson bracket, which relates position and momentum, the classical variables, not operators, which is 1, and also that the evolution of any operator, which is some function of these x and p, is just the Poisson bracket of O and H. Now let me ask you a question. Does the left-hand side here look analogous to the right-hand side? Yes, these look a lot alike. And this is precisely the observation that Dirac made. And so he came up with a very simple rule. He said, well, you know, these kind of look alike, so why don't we take the Poisson bracket and supplant it by the quantum commutator, modulo this IH bar, which is indeed very important, and I should maybe underscore it here. And all you have to do is take any classical operator, whatever it is, and just supplant its Poisson bracket by this commutator with IH bar. And you might ask, well, what is the justification? And there's very interesting, if you look read Dirac's book, The Principles of Quantum Mechanics, a wonderful book, he says, there is, however, a fairly general method of obtaining quantum conditions applicable to a very large class of dynamical systems. I mean, after all, quantum physics is supposed to describe everything within classical physics, so I can take any microwave or any spring or any pendulum and try to describe it using quantum physics. And he says, however, this is a method of classical analogy. And really the way that we can do these quantizations is through this method of classical analogy. And this is why we've gone through this in-depth discussion of the classical oscillator in classical physics before jumping into the quantum one, because so much of this is based on analogy through classical physics. And quantum now adds some richness on top of that, which simply does not exist and is inaccessible in the classical world. For the very advanced view, I will point out that if you do this, you'll observe that even though all quantum algebra follows from this simple rule, Dirac's derivation, based on 3 conditions, which, if you're interested, you can read in detail, runs into problems, such as how do you deal with products of operators x squared times p versus p squared times x? Well, it turns out it's inconsistent and it's not generally possible. So while it's very powerful and works pretty well, it doesn't really always work, and things are more subtle. And there is no general solution that I know of to this day to handle the general case. You might find that a bit disappointing, but I find it I find it a nice, interesting, open reason, and it ties in very closely with, say, things like quantum gravity, where you have to quantize things in a curvilinear space, right? Not in a Cartesian coordinate system. So having made this link and maybe stated a slightly disappointing conclusion to a procedure that's very nice in general, but actually breaks down in many interesting cases, I'm reminded of this quote by Albert Einstein, which has often kept me going. If I knew what I was doing, it wouldn't be called research. And I think that's part of the spirit of research, is being exploratory. And so that brings us to apply Dirac's canonical quantization onto our classical system. And so following the prescription inscribed on the previous slide, all I have to do is now supplant the classical variable phi of t by a quantum operator phi, the classical variable q of t by a quantum operator q. Similarly, the Hamiltonian function of the position and momentum q turns into a Hamiltonian function of position operator phi and position operator q. The commutator of phi and q, or sorry, the Poisson bracket of phi and q turns into the commutator of position and momentum, which is IH bar times the identity. And also importantly, the Poisson bracket of alpha and alpha star, which I didn't have the time here to get into directly, but you can obtain by following this, phi and q, it just follows from that, is equal to, in the quantum case, the commutator of A and A dagger and 1 hat. Notice that alpha just turns into A hat. And so these simple few relationships form our quantum bridge from the classical to the quantum world. Now that's a lot of math and algebra, and let's remind ourselves that the commutator in quantum between A and B, I think as was discussed in the first lecture, is defined as A times B minus B times A. The Poisson bracket, if you're wondering, as a sort of extra piece of information here, is defined in a similar way, except that there are derivatives which have to do with the structure of the phase space. And so the Poisson bracket of A and B is similarly A times B minus B times A, except that A and B have these partial derivatives. So it's the analogous classical operation to the quantum commutator. But moving forward, we can now summarize that in the classical world, the Hamiltonian of the classical oscillator is q squared plus phi squared, is 1/2 h bar omega a star a plus alpha star. In the quantum world, very similarly, all we do is basically rewrite those exact same expressions and put hats on them. Nothing has changed so far. In the classical world, the phase space we describe by a point as alpha of t, which was described by the square root of 1 over 2 h bar times z. Z is the impedance, which is the root of L over C. And it then depends on the position plus I times the impedance times Q. There's a particular scaling here, you notice, that goes like square root of Z inverse and square root of Z between position and momentum, and that's required for phi and Q to be canonical. And in the quantum case, again, all we do is replace the operators phi and Q by phi hat and Q hat, or the variables phi and Q by the operators. You might be also wondering, why is there no time dependence anymore? You see that on the left-hand side I've been writing phi of t, Q of t. On the right-hand side it's phi hat, Q hat, there's no t. Well, that's because we've done the transition in the Schrödinger picture, in which the operators are stationary and it is the wave function, the state psi, that is evolving. We can make an analogy also to the classical way by saying in the classical world, the time evolution of this operator A alpha of t is just the initial condition times e to the minus I omega naught t, where omega naught is the resonance frequency of the oscillator. In the quantum world, within the Heisenberg picture evolution, we can write the exact same corresponding evolution of this bosonic annihilation operator. So alpha of t, so A of t hat, the lowering operator, evolves in the Heisenberg picture just like the classical alpha degree of freedom. And I don't even need to necessarily derive the equations of motion here because I can use the correspondence principle that Dirac introduced. Just for completeness, I'll show that if you want to go between flux and action angle variable alpha and back and forth, you can again do that. You can rewrite phi as a sum of the anharmonic of alpha star plus alpha. In the quantum world, I've now defined the exact same relationship, replacing alpha with alpha hat, and I've introduced a constant called phi ZPF. Phi ZPF is just equal to what you see here on the left. However, it has a very important physical meaning that I'll explain in the next few slides of the quantum zero-point vacuum fluctuations. It's essentially the root mean square fluctuation, but we will get into that in the next slide. And it just again equals the square root of h bar z over 2 from the classical world. And for completion, I'll give the charge as well, which looks like this. Now, the very key operator in all of this that will allow us to form a very convenient description for explaining all of the effects is the bosonic operator A. This operator A acts in a particular way, like some of you anticipated in the questions I saw. Suppose that we have the very lowest energy state, right? N equals 0 that we anticipated before. Then this operator A, acting on that state, will give you 0. It destroys that state. Acting on the one state, it will take the one state and demote it to the ground state. And so it annihilates the one state into, or it annihilates the 0 state into nothingness, and then it demotes the one state into the ground state. If you dagger it or apply its adjoint here, then it does the inverse operation in a way. Not quite the inverse, but inverse in a conceptual way, where it takes the ground state 0 to the excited one state, and it takes the one state into the next state 2. So it creates a photon. So the annihilation destroys a photon, whereas the A dagger creates a photon. And so in general, you can show, and I think we can just take these right now as basic givens that you can show from the commutations, that when applied to one of these Fock states or eigenstates, which we'll picture in a minute, there is a certain hopping scheme. So between each energy level here, when I destroy a photon in the oscillator, since each photon corresponds to one excitation inside of the oscillator, when I destroy a photon, that takes me from this ladder down by 1, and it gives me a square root of n. And when we create a photon using A, that takes me, that's the operation of A dagger, and that will give you a square root of n plus 1 factor. Often we get asked in this lecture, how now do you write these in terms of matrices, right? Things that are very familiar. Well, the lowering operator you can certainly express by saying that, well, it takes the state 0 into a column of all zeros. It takes the state 1 into the ground state with a coefficient of 1, right? It takes the state 2 into the state 1 with a prefactor of the square root of 2, it takes the state 3 into the state 2 with this prefactor 3. So I'm on the columns here, I'm writing the basis vector of what comes in, and on the rows I'm writing the output vector. Or in other words, we can say that A hat is equal to the sum over n is equal to 1 to infinity of the square root of n, and it takes the state n plus 1. Oops, I seem to have messed up my numbers here. This should be, I don't have an eraser, so I will just rewrite it here. Takes the state n to the state n minus 1, like this. And this is the operator version of this same matrix equation, which follows from the hopping terms defined above. A dagger is just the conjugate transpose, so you flip over the diagonal. And the other key thing that we will need, which describes the energy, as we'll see, is A dagger A. And that's how many photons are in the oscillator or in a state. That's the operator. Okay, and now we can use these relationships to calculate a few basic properties of both the Hamiltonian and as well as the operators of phi and q in order to show what the expectation value of the flux in different Fock states is. Now, if you're wondering at this point, what is a Fock state and where exactly did it come from, remember that we have a Hamiltonian, H. That Hamiltonian must have some discrete energy levels, as we saw now a few times. So I can write out that it must have some energy levels which say go as the level 0, the level 1, and so on, the level 2. And so these Fock states n represent eigenstates of the Hamiltonian H. And because the Hamiltonian H is the product of A dagger A and AA dagger, if you look at the previous matrix here, you see that this matrix A dagger A is diagonal in this basis. And so that when we apply the operator H on any of these Fock levels, of course, we get what we will, the following. Let me now switch over to do some calculations. We can say that the Hamiltonian H is equal to h bar omega over 2 times A dagger A plus AA dagger. And I will suppress the hats in the following. We also have the relationship that the operator A dagger A applied to a Fock level n is equal to n times n. In other words, the Fock state n is an eigenstate of this operator. How do I know that? Well, if we looked at the previous line, which which we can decompose like this, A dagger applied on A times n is nothing but the square root of n here times n minus 1. And we still have the A dagger operator to apply. And now using, again, the fact that A dagger applied on n is equal, let's call it n prime, is equal to the square root of n prime plus 1 applied on n plus 1. So it raises the state. And so if we use this again, then we can arrive at the fact that we have the square root of n plus 1 minus 1 times the square root of n applied to the state n minus 1 plus 1. Hopefully this is making some sense here. essentially we obtained the usual relationship of an eigenvalue having started with a dagger a times n gives us the Fock state n again, so it doesn't change the wave function, but it does give us a prefactor n, and so this is the eigenvector and this is the eigenvalue of this operator a dagger a. Of course, the Hamiltonian is just composed of a dagger a and a dagger. We can repeat the same procedure for a dagger, or equivalently we can use the commutation relationship I showed above, which was that a comma a dagger is equal to 1, or in other words that a dagger plus a dagger a, and of course this is a minus a dagger a is equal to 1, to say that this funny combination of a dagger is equal to 1 plus a dagger a, which is the photon number operator, as we saw above. From this expression highlighted in yellow, we can see that a dagger a is really equal to the photon number n. It's the number of excitations. All right, exploiting this in the Hamiltonian, we can then rewrite the Hamiltonian h as h bar omega over 2, and we had a dagger a plus a dagger. And now using this expression in here, we can obtain the following: h bar omega over 2 a dagger a plus a dagger a plus 1. Or simplifying the two a dagger a's, we obtain h bar omega over 2 times 2 a dagger a plus 1, which then simplifies to h bar omega a dagger a plus 1/2. All right, now this is the famous energy of a harmonic oscillator, where you see that we have two terms. We have the term which says, let's add this, we have the term that says how many photon excitations are inside of our oscillator, and we have the term that says that even if I have 0 excitations, then there must be at least half an energy, or as we like to say, half a photon of h bar omega inside of the oscillator. So we call this the 0-point energy. And that will be related to the 0-point vacuum fluctuations. Now, if you're wondering what is the value n, we saw that the energy potential of the classical harmonic oscillator looked like this. So the lowest energy you can have was some level in between here, which let's say I'll call at some quantized energy level spacing like this, where this parabola represents the potential energy. So let's say phi squared over 2L, and on the horizontal axis here we have phi, the magnetic flux, right? And this is 0 magnetic flux, this is now some positive magnetic flux. This is the 0th level, the first excited level, the second excited level, and so forth. So this now connects with the semi-classical picture we had. If we apply the Hamiltonian now on a Fock state n, we obtain the energy of the nth state, let's call it E sub n, which is h bar omega naught n plus 1/2. Okay, and this was the semi-classical picture of n we used earlier, where n, of course, is equal to 0, 1, 2, or some other number. Now, an interesting question happens. In the classical picture, we had a phase space of phi and q, and we could identify the oscillator with a particular point in that phase space. What about here? What is the mean value, or what is the average value of the position and the momentum? So we can calculate, try to figure out in the quantum case, what is the mean value of the position. And the way to do that is to take the expectation value of the magnetic flux, say, which is our position, and write it out. Let's say for a Fock state n, we can write out that the magnetic flux was, if you recall, phi ZPF times A plus A dagger applied on n. Phi ZPF is some number. Well, we actually know what it is. That number is equal to the square root of h bar z over 2, where z is equal to the square root of L over C. That's the impedance of the oscillator. So it will set the scale of this. If we now apply the following, we have to maybe first show that the expectation value of n applied on A on n is equal to the square root of n times n minus 1. Of course, you recognize that this is equal to 0 since eigenstates of the Hamiltonian are orthogonal. We can similarly do the same thing for the raising operator and see what is the expectation value of A dagger applied on the coherent Fock state here, and we'll see that it's the square root of n plus 1 times the overlap between the nth Fock state and the n plus 1th Fock state, and that likewise is also equal to 0. In other words, if we return to the expression for phi, the mean value of the position or the magnetic flux, we see that it's phi ZPF times the expectation value of A plus the expectation value of A dagger, which is equal to 0. So on average, phi hat is 0 for any Fock state. So independent of our Fock state, the mean value of the magnetic flux is actually always 0. So in this phase space picture, we on average find ourselves always at the center, if you want, for phi. Well, I haven't actually shown that it's the center, maybe, because we have to also calculate the position q. But you can see pretty easily that since q is equal to minus I q ZPF A dagger minus A applied or sandwiched between these Fock states, the expectation value of q is also equal to minus I q ZPF applied on the expectation value of A dagger minus A, which is again equal to 0. So it doesn't even matter what q ZPF is or phi ZPF is. For completeness, I'll just remind ourselves that q ZPF is equal to the square root of the complementary to what phi ZPF is, which is h bar over 2z. Now, in quantum, we saw that the oscillator still has energy, right? So if the magnetic flux and the electric charge are both 0 on average, where is the energy, the half photon and the nh bar omega, coming from? Well, they come from fluctuations. So we can look at now, say, the variance of these operators. And because the mean of these operators is 0, it follows that the variance of this operator phi hat is going to just equal the expectation value of phi squared minus the expectation value of the mean squared. Up here, of course, we just showed that on average the magnetic flux is 0. So in these quantum oscillators, on average, if you measure it and integrate, you'll see that there's no magnetic flux. However, if you look at the fluctuations, which is the phi squared, you'll see that those are non-zero. How do I know that? Well, we can write this out as, say, n, and we have a dagger plus a squared sandwiched by n times the 0-point fluctuation magnitude squared. Expanding, we can find that we have a dagger squared plus a squared plus a dagger a plus a dagger applied on n times phi ZPF, which we can then again write out as n applied on a dagger squared plus dot dot dot. I'm not going to write all of them out because I just want to point out that this a dagger will turn this n into n plus 2 times some coefficient, but then sandwich with n. So this term will be 0. Then the next term, which is a squared expectation value, will likewise be 0 since we have to hop. And then with the next two terms are the ones that will not be 0, and these are the a dagger a plus a dagger expectation value, and then times again phi ZPF squared. So coming onto the next line, we can use, and let me maybe move the phi ZPF to the front to make it a little bit neater. So we have phi ZPF squared times the expectation value now of a dagger a plus a dagger, which looks just like the Hamiltonian. Earlier we showed that through the commutation relations you can flip this around to write a dagger as a dagger a plus 1, which then leads you to write out and say that you have 2n plus 1 times phi ZPF squared. And if you remember, this is equal to the expectation value of phi hat squared, or is equal to the variance of the operator phi. Now for the Fock state, n equals 0, we see that the 0-point fluctuations of phi hat are now equal to, oops, we missed the square there, are now equal to phi ZPF squared. All right. So in other words, the root mean squared fluctuations of the magnetic flux phi are equal to, or in other words, the standard deviation of the operator phi for a Fock state, for the ground state, let's say, let's focus on the ground state, are just equal to phi ZPF. And that's exactly why we call phi ZPF the 0-point fluctuations. So what does that mean? That means that if I was trying to measure what the magnetic flux as a function of time was, let's say, measured, of the oscillator, what I would see as a function of time is that the magnetic flux is some value which fluctuates. And I'm just trying to represent now a noisy signal which has a mean 0 and a standard deviation of phi ZPF. Now you might be wondering what exactly is the value of this magnetic flux and how large are these fluctuations? It's not too difficult to show maybe that these fluctuations can be, in the voltage can even be at the level of microvolts, even if you set up things large enough, so they can be macroscopically observed. But maybe more importantly, we can see that, oops, and I see we have switched over here to the PowerPoint already. Apologies for that. Right? Let's switch back. This is the flux. Now, what about the charge? The charge does the exact same thing. So you have, again, a Q of t, which will look very similar. They will be here independently measured, but you have, again, some sort of fluctuating signal. This is not supposed to be a regular signal. It's just difficult for me to draw a random signal, which has fluctuations, again, that has QZPF, like that. So at this point you might be thinking, well, this looks like a very noisy random signal for both flux and charge, but there's more to it. And this gives specifically the energy of the half photon of noise. It's this type of fluctuation. And that's another way to say that the atom can never be at rest. The electromagnetic oscillator is never at rest. Even when there are no quanta of energy in it, there's always a rest energy, a 0-point fluctuation. It's always there in that way. Now, how do we interpret that a bit more physically in here? So if we return to the nice picture we had of the potential energy of the oscillator as a function of the magnetic flux, which is a parabola, we can plot the kind of discussion we just had and generalize it to describe what the probability density or the wave function, which is the probability amplitude, looks like for the ground state and for the first excited Fock state. Okay, and so this is the kind of thing I recommend you to see in the references on how exactly these get derived. But what we just proved was that on average in the ground state, the mean expectation value of the magnetic flux here was 0. So you see something centered on 0. However, it has a standard deviation, a variance, phi squared, of phi ZPF squared. This is the variance. Right. Now the first excited state is orthogonal to the ground state, and so it has a node at the center here, and it has a larger variance. Right, and then each of these curves here is shifted in the vertical axis representation of the wave function in the position or the flux basis. So it's the overlap between the nth Fock level and the magnetic flux phi. If I zoom out and try to show you a few of the higher levels, you notice that they're quantized in units of h bar omega. So the difference here is h bar omega in terms of energy. The difference between the first and second level is also going to be h bar omega naught. Difference between the second and third level will also be h bar omega naught. And here will also be h bar, oops, that arrow is a little too long. And each higher Fock level has an extra node and is orthogonal to the previous one. These are Laguerre polynomials. Now, to understand the picture better, we have to look at both position and charge. And to do that, we can return to the earlier picture we had of the simple harmonic oscillator in phase space. In phase space, the simple harmonic oscillator at a fixed energy was represented by a ring centered at 0, 0. And the particle, the state, would oscillate around this ring. Now in the quantum world, that's no longer quite the case. So here's a representation, a particular picture I will draw of the ground state. For the expert in the audience, this is called the Q function. For the rest of us, I think all we need to know is that the brighter the color, as indicated here by this chart here, the brighter the color of this picture, the more likely we are to find the particle, the harmonic oscillator, at this particular position, so to speak, in phase space, where on the x-axis we have the magnetic flux, on the y-axis we have the charge Q. So in the ground state, if I try to plot the probability density of finding the particle at this particular flux and charge, or this particular position of momentum, I can't actually quite do that because of the non-commutivity, or it's the difficulty in the simultaneous measurement of two non-commuting observables. But I can give a quasi-probability, something that looks a lot like a probability density for the joint distribution. It's not quite that, but I think for our purposes we can think of it as a close enough representation to say that, look, in the ground state I'm very likely to find that the photon is down here at 0, 0, right? That there's 0 charge and 0 flux. And on average that's the case. However, it fluctuates, right? We have a cloud of probability. Just like in an atom there's a cloud of probability, this should look a lot like an s orbital of atoms. The cloud of probability says, well, sometimes I can find the atom to have a to have a position of negative, x and negative and some q over here, or sometimes it's here, sometimes it's there. It's most likely to be in the center, but it can be almost anywhere. If the region is very, very dark blue, it means it's almost never going to be found there. If it's very white, then it means that it will be found there very often. And that's the ground state. And that's the picture of the inner ring here of the classical harmonic oscillator. In the excited state, or the first one state, that's going to be the first trajectory. Okay. Now what you see is that what we've done is basically take these rings and give them some width. Right? The particle seems to fluctuate around these somewhat classical trajectories in this case. The ground state just happens to, the ring is so small relative to the width that it kind of collapses on itself and it looks like a circle or a Gaussian. For the first excited Fock state, however, we see a donut. If you're in the first excited Fock state, because you have energy, because you have excitation, you can never find the particle to pretty much be in 0, 0, to have 0 charge and 0 flux, because it's excited. You will tend to find it at some orbit over here, and this orbit will be very related to the classical, this orbit over here will be very related to the classical phase-space trajectories we drew earlier. However, in the classical world, we had this oscillation where the particle just goes in a deterministic fashion and rotates deterministically clockwise as a point. In the quantum world, that's no longer a valid interpretation. We have rather this cloud of probabilities. Now, the oscillator can be found to have a position and a charge that's somewhere in this ring, right, with some fluctuation, which, by the way, this fluctuation here, let's erase that. This fluctuation here in phi is given by exactly the 0-point fluctuations, phi ZPF. And the fluctuation in charge here is given by Q ZPF. but otherwise it's a kind of random stochastic. You know, the particle can be here, here, or you know, it doesn't follow the same kind of classical trajectory. So this is one of the differences, the key differences between classical and quantum. Now, it's not just a pure stochastic, you know, noisy thermal type of evolution, because you can also create superpositions of, say, the 0 and 1 state. So if I created a state which has 0 plus 1, I would find a function that's somewhere in between these two, but it has certain non-classical correlations that you can only find in that case. Okay, and I see, Brian, that we are running up very close here on the hour. So we're almost done now with the harmonic oscillator. So maybe I will pop up a question for the readers, which will be something you can think about for tomorrow. The flux and charge operators are both Hermitian observables. So how can some expectation values of flux and charge be imaginary, or others be negative? For the very advanced reader, I will leave this as a problem set, and maybe I'll discuss the answers at some point on my To Become blog. You can think about those if you're in the very advanced group. Otherwise, think about this question. And I think in the meantime, I will pause and open it up for questions and pick up the rest tomorrow, where we will dive into the transmon qubit and see how all of the things we learned about the harmonic oscillator will translate very straightforwardly almost to an anharmonic oscillator, which will allow us to space the energy levels in a nonlinear way, create a qubit, then control it and manipulate it.